So I want to start with giving some kind of context and why we started thinking about these kind of theorems and questions that I'm going to talk about. So I would say, so with we, this is joined with, it's a work in progress with Tarkov, Kontsevich, and the Pandit. And it kind of grew out of another project that we're working on. And so the question we were thinking about is how to make sense of notions of Kähler geometry in a kind of categorical context, so for Kaya categories and derived categories. And in particular, I kind of want to give some sort of parallel between the A model on one hand and kind of a toy model for it, which is a quiver representations. So on this kind of side, we start with a Kähler manifold M omega, some holomorphic n form and symplectic form, not necessarily a Calabi-Yau condition. And here we start with some quiver and should have a central charge, so just some complex numbers in the upper half plane for each vertex. So Q has some set Q0 vertices, Q1 of arrows, and for each vertex, the number in the upper half plane. Those are kind of the periods of this manifold in some sense. And so the basic object here to study inside M is Lagrangians. And what that corresponds, so kind of here what I'm saying is always sort of approximation. I mean, if you want to really make this, like you should really have all this extra data that you have for Kaya categories. But it's not going to be too relevant for my talk, so I'm just stay at that level. And here, so what I want to maybe understand as a metrized object is here a metrized quiver representation. So I have some vector spaces and maps. So if alpha is an arrow from I to j, then a representation of that quiver has a map, has a bunch of vector spaces for each vertex, and maps from vi to vj for an arrow from I to j. Plus, so the whole thing should be metrized, so I have a Hermitian metric on each vi. Okay, so these, I mean, sort of why I need to, so the metric here, deforming the metric on the representation, I want to say corresponds to deforming the Lagrangian by a Hamiltonian isotopy. So maybe that's not entirely convincing why these two things should be parallel yet. So where the Kähler geometry comes in is that I have a Kähler potential, which turns out to be complex valued. So here I have S, some set of Hamiltonian isotopic Lagrangians. Going to complex numbers. And it's sort of defined indirectly, so it's really sort of by its differential, maybe a one form. So ds of some function f. So if a tangent vector on here is, there's an extra parameter which corresponds to, but roughly speaking, a tangent vector on here is a function f on the Lagrangian. at a point L. So up to an extra parameter, which I'm also ignoring here, which is the constant functions. And so the exterior derivative of this functional on a tangent vector f is given by integral over L of f times this omega, a holomorphic n form. And so the corresponding thing here is you have sort of metrics on a fixed representation. Again, going to complex numbers. And there's an explicit formula in this case.
F should be defined up to constants?
So the tangent space here, you're right, is really functions up to constants. Yes. But I can, so if you want, you can change this to being this lift to some S1 pre-quantum bundle over the Lagrangian, then you have an extra parameter of this space. So, yeah, so really this should be, I mean, I'm not going to talk too much about this side, but yeah, you're right. So really I want sort of an extra parameter here in the moduli space so that the tangent space is really C infinity L. But it's not going to matter too much. But what the constant functions here correspond to.
So this has no critical points.
This has, well, sort of critical points. Yeah, so a Lagrangian of, a special Lagrangian of phase 0 will be a critical point. Yeah. And in general, just if you take the, I want to take really, so this is a complex thing, and then I get a bunch of real valued potentials by taking real part of E some phase, and this thing will have critical points. So I'll say that in a moment. But so first, yeah, what's the corresponding thing here? Here's an explicit formula, so it will be some sum over vertices of these Ci log determinant of Hi. Right, so here is sort of hidden a reference metric, just like here, sort of also choice of base point involved if you want to integrate ds. Minus sum over arrows, trace T alpha, start T alpha. So it looks like a standard Kähler potential on a vector space. So the next, so this S is something on metrized objects. It also kind of varies, actually a bigger moduli space of all objects combined. Yes, I'm saying there's a kind of implicitly there's a reference metric and it's determinant of Hi mod that reference metric. Kind of up to scaling. I mean, scaling this will just change this by a constant, so up to constant is well defined. Set I is just some complex number in the upper half plane for each vertex. There. It's a central charge. Yeah, then, so in both cases, there's a flow on this space, which here, so is minus argument of omega restricted to L. That's like a mean curvature flow. And here, so I mean, once you have this, sort of the rest is all derived from that formula for S. S sort of determines the geometry. Here the flow is H minus 1, H dot, minus argument of D of S, so that turns out to be some over vertices, Ci projection to the space Vi, plus a sum of commutators. Okay, so this expression here just comes from computing the exterior derivative of this S up here. Yeah, so this is a matrix, and it has some polar decomposition, and argument is E. So is that here actually is a normal operator? So you can think of just diagonalizing it and taking argument of the diagonal. But in general, argument makes sense for matrices by polar decomposition. And it doesn't matter, there's two polar decompositions a priori for a matrix, depending on the order. But this is actually independent of the order, the argument always. So what does this flow do? It decreases. Yeah, here this is always, it has a spectrum in the upper half plane, so there's no ambiguity. Yeah, good question. Yeah. So so in both cases, there's also a mass which is decreasing under this flow, which is integral L, absolute value of L restricted. And so if we restrict omega to L, then we can make sense of its absolute value. And integrating over L gives essentially kind of a volume of L. And here it's a trace norm of this same guy here. And so what you can show is that this is always, in both cases, decreasing under the flow. Okay, so I mean, sort of the motivation for this flow sort of comes from the A model. We want to have something similar. And so the fixed points of the flow, at least are up to rescaling, so where the flow is just acting by rescaling the metric, or here kind of this is constant. Here are special Lagrangians. Right, it's kind of, it just means that this here is constant phase. And over here we get some kind of analog of special Lagrangian, which is harmonic metric, what's called. This is some work of Alistair King. So some preferred metric, and which exists if and only if there's kind of like a finite dimensional DUY theorem. It exists if and only if the representation is VI T alpha, if this is polystable. So polystable means what? Well, this number Ci in the upper half plane on each vertex, they define a central charge, and so you can talk about slope stability of representations. And polystable means it's a direct sum of stable objects. And it's kind of unique up to rescaling on each stable summand. But the point is there's kind of a completely algebraic condition for when does this harmonic metric exist, so the fixed point of the flow. Here it's going to, well, there's some conjectures, but if you really want to make them precise, you need to start talking about Fukaya categories and all this extra data you have on special Lagrangians. But I mean, very roughly, if you make all of this, not just this kind of simple-minded definitions, but sort of enhanced, it should be semi-stable or polystable objects in a Fukaya category, which is proven in one dimension for surfaces, but higher dimensions fairly complicated, which is why we're taking refuge in this quiver world here. So the point is, so the question we're asking is what is, so this is polystable, so most representations are not polystable, and what's going on with this flow in the case when there's no fixed point. So the question here is, what are the asymptotics of the flow for non-polystable objects? Which I'm going to answer, so in this case, and here, a more conjectural picture. So the point is that just like here, there's a purely algebraic condition that you can check to see if a fixed point exists. These asymptotics are also controlled by an algebraically defined data. So, the answer here is roughly that there's algebraically, these asymptotics are controlled by, I'm going to make more precise what that means, by an algebraically defined refinement. So sort of your first guess might be that the Haiden filtration should control this, but it's actually a refinement of the Haiden filtration. So that the same filtration that appeared in Ivan's talk yesterday. And this has kind of two big features. The definition turns out a little bit complicated, but I mean, the kind of most important features is that one, so in Haiden filtration, the subquotients are always semi-stable, and here the subquotients are polystable. It means if there's a semi-stable piece in the Haiden filtration, it has a further filtration into polystable guys. And second, so it's the Haiden filtration is indexed by real numbers, slopes or argument phases. And this thing here, it's indexed by R infinity, which turns, so we'll see, you want to think of this as R plus R log t plus R log t, and so on. So iterated logarithms and then arbitrary finite real combinations with the standard lexicographical order. Right, and the reason for having these logarithms here is that the asymptotics will behave like a function in here. Okay. So there's again two main features. There's some interesting stuff going on there.
So, Fabian, in cases where you can understand certain Fugate categories as representations of a quiver, do you have maps in either direction for these moduli spaces?
No, it's more of an analogy here. Right, since one is infinite dimensional always, the other is always finite dimensional.
But there's no projection or injection of one to the other?
Not really naturally that I know of, no. Yeah.
I mean, you know, so you wrote down these functions, and is it then the case that flow is the gradient flow of the argument, and that then the modulus is preserved or something? And what's the structure?
The flow is the flow is determined by, it's roughly, it's close to the gradient flow if I take some real part E times I phi times S. I mean, it's roughly like the gradient flow of S if I make it a real value.
Hamiltonian interpretation that gives rise to a conserved sorry, it's a decreased length.
It's more like a parabolic flow or like Morse theory. Yeah. And it's kind of think of it right like a heat equation or some kind of thing, converging to something stable. So when I say algebraically defined, there is actually a quite general context in which this makes sense, which we found, which is in lattice theory. So if L is an artinian lattice, which means it's a finite length modular bound lattice. So for maybe not. So what does this mean? So right lattice is something that you have some join and meet operations. Bound means just that you have some 0 and 1 idempotent neutral elements with respect to these operations. Modular means if A is less than B, less than or equal to B, then there's two different projections to the interval from A to B, which should be the same. So X meet with A, join with A, meet with B, will be the same as the other way around. So first you meet with B, and then you join with A. Okay, so it goes back to like 100 years. I mean, roughly, so finite length finally just means that there exists some maximal chain of finite length. So.
Can you say this in terms of categories in case I haven't seen this before?
Well, I mean, maybe so if you've never seen this before, maybe a good way to think about it is you have a vector space and then you have some collection of subspaces, which are closed under, taking intersections and sums. And then this will be an example of such a thing. So, like, geometrically, that's how you think of it when you work with that. Okay. Now I'll say how this relates to the stability and these things. So besides the modular lattice, there's another sort of ingredient which is coming from the central charge. So I mean, there's something like a K group of the lattice, which will be a group generated by L, and with this relation coming from inclusion-exclusion principle. So A plus B is A meet B, A join B, which contains kind of a positive semigroup, which is generated by intervals, so by y minus x for x less than y in L. So you think of this like it's a K group of your category, and this is like classes of objects. And so the second piece is a function, homomorphism y from this positive semigroup to positive real numbers. There's roughly like masses of objects. And so how does this relate to what I was saying before? Let's see the example here. So number one, if you have a category with Bridgeland stability, so C is a triangulated category. this is a bridge instability condition. And you have, you fix some phase and look at some object E, which is semi-stable of phase phi. So the C upper phi was, if you remember from Ivan's talk, this is the subcategory of objects which are semi-stable of phase phi. And this is always a finite length category, an artinian category. And then the lattice L will be just the lattice of sub-object of this semi-stable object in this category. Sub-objects of E in C phi. So there's a part of the definition of a bridge instability ensures that this is a kind of finite length. You cannot have any arbitrarily long chains of sub-objects. And the operations are just intersection and sum. So coproduct and product. This is an abelian category. So you have products and coproducts. So essentially, like if it's representations of a quiver, then it would be like.
So just find the product is one of the operations.
Well, I mean, they're all sub-objects of the same object, so you can define unions and intersections. And this Y is just coming from the central charge, so it's the real part of E minus I phi, rotated to make it phase 0 times C. Yeah, so that's one example. Then it turns out there's some kind of other, other modular lattices which don't come from Artinian categories, which are like, for example, if you take normal subgroups of a finite group. Yeah, and I should say there's always a kind of canonical choice of what this Y is, which is just the rank of the subobject. So we can always take that, but here we take something other if it comes from stability. Finally, so an example that Kancevich told me, if you take sub-bundles of fixed slope of a semi-stable Arakelov bundle, it's like a vector bundle on the ring of integers inside some number field, and Arakelov bundle is like it's equipped with a metric for each Archimedean and non-Archimedean place. And then there's a notion of slope stability, and this is again something that doesn't really come from an abelian category, but it fits into this kind of general framework of modular lattices and that we set up here. But yeah, mainly I'm going to be interested in this example 1, which is coming from bridge instability. And so the result is that so in these cases there's kind of a canonical filtration. So it means like a chain in this lattice. Which depends on this function y. So there's a few parameters. So theorem. Well, not going to make it completely precise in the context of lattice theory, because maybe not. Yeah, it's not very intuitive to formulate everything in terms of lattices, but I'll say precisely what it means for in the abelian context. So there exists a canonical. So given, yeah. So given this L and Y, this artinian modular lattice and function of Y, there exists a canonical chain A0, A1, AN, and there's some indexing, lambda 0, lambda n, which are in R infinity, such that, so I mean, saying the canonical, right, there's actually a precise definition of, so there's a unique characterization of what this chain is, and I'm going to say here roughly what it means, and then exactly for abelian categories, so that these intervals from ak to ak plus 1, so this is roughly like sub-objects of a subquotient. They should be semi-simple, so that means this should be a complemented lattice, a lattice which has complements. So any element in the lattice has a complement. And it has a kind of balancing condition. Set the sum over real numbers, lambda times y of, over k, lambda k, and here ak minus 1 is 0. And then there's a kind of stability condition on this chain. Yeah. So I don't want to say exactly what that is. You can ask me after the talk if you're really interested in general lattices. But again, so maybe the most important example for now is if A is some artinian category. So this lattice is sub-objects of a certain object in here, and Y is going from K0 of that category to R. And so the theorem then translates to, I should say something. There's a construction. There's another category, A tilde, which is again an artinian category. Which has objects, a pair of E and A, where E is a R-graded semi-stable object, semi-simple. Think of it like the associated graded of your filtration. And A here is some extension data. So E is some sum of E lambdas, so it's R-graded. And A is some extension data, so A should be in X1 of E lambda plus 1 to E lambda. And morphisms are just a thing you would write down, intertwining morphisms in here. And this category, again, has a central charge, which is a sort of deformation of your original central charge. So C, which is sum over lambda in R of lambda times y. Let me take the formula of lambda plus I times y of e. So we can talk about stability again in this new category. And y is like, yeah, it's like your central charge, but the central charge is just on the imaginary axis. So, I mean, in general, this A is, right, it's the category in the Bridgeland context, it's the category of semi-stables of a certain phase. If I restrict to the central charge to this category, it will have just one. Will be really essentially a function to R instead of C, and that's what y is. Okay, so the theorem is essentially a special case of this thing here, which I didn't make it completely precise, that so there exists a unique, what maybe we call balanced or weight filtration on each object of this Artinian category. Such that, so it's the following condition. Filtration, let's call it x less than or equal to lambda are the pieces of the filtration. So, so first of all, the length 1 associated graded object should be semi-simple. So x less than or equal to lambda plus 1 mod x less than or equal to lambda is semi-simple. And the second condition is that, well, I can define an object in this A tilde. So there's x tilde in A tilde, which essentially it's like taking the associated graded of this object, but remembering some of the extension data also. So it's so x tilde lambda is x less than or equal to lambda mod x less than lambda. And then there's a natural extension class in here, determined by the filtration. Sorry?
Is x less than lambda the colimit among all lesser ones?
Yeah, I'm assuming that x is a complete filtration. So I mean, it's an Artinian category, so there's just finitely many steps in any case. So yeah. So there's an extension class here, just determined by the filtration if you basic homological algebra. Which is kind of this data is sort of it's a little bit more than the associated graded, but it's less than the object itself. So you can't recover the original object just from this data. It's something in between, kind of like a dominant term of your extension. And so this is an object, and if this, so the second condition is this is in A tilde is semi-stable in this, right? So I defined a central charge on here, so it makes sense to say it's semi-stable of phase pi over 2. So central charge is purely imaginary. And so that's the second condition. So the claim, yeah, it's not true. It's a bit strange condition, but it's justified by the fact that really there exists a unique such thing. And the way to prove that, you construct kind of like a space of all the various filtrations on your object, and then you have, again, something like a mass function for every filtration. So every filtration has a kind of mass. And you minimize this, and there exists some unique minimum, which will be this filtration. Yes, and maybe to give an example here, this relates actually to something that, so there's a special case here that is quite well known in theory of Hodge structures. So if V is a finite dimensional vector space, and N is a nilpotent operator on V, then there's something called, so this is like a Lefschetz operator, and there's something called the weight filtration of that operator. So it looks like if you have, this here is weight, and this is 1/2. So if you take each Jordan block of this nilpotent operator and you sort of put it in a balanced fashion centered around 0. So if these are basis elements, these dots are basis elements, then so it acts by decreasing weight of the element, and the whole thing is balanced around weight 0. Okay, so this filtration here, which exists, is unique. This is, so the filtration is the weight filtration of a nilpotent operator. Which was originally appeared, it was defined by Griffiths, and then later used by Schmidt. So this is the filtration if you have an isolated singularity. And there's a kind of mixed Hodge structure on this Jacobian ring, and you need so you have a mixed Hodge structure, you need a weight filtration, and this is the filtration you take, where N is your monodromy, or logarithm of your monodromy. Okay. Well, that's why we call it a weight filtration. This is the special case. So, but in this example here, there's no dependence on this function y. So I want to give another example, kind of what's going on in general. And there's a kind of interesting thing here happening is that you have, again, like you used in stability, you have a wall crossing phenomenon. There's some kind of wall and chamber structure on the space of all possible y's. But these walls are now nonlinear. They're not linear subspaces, or affine.
Sorry, can you say what are the axes on that picture you just drew?
Well, this axis is kind of nth Jordan block, in a sense, and this axis is the weight. So it's the indexing. So you imagine sort of each Jordan block, and then you grade the basis elements so that it's centered around 0. Maybe I should mention before I gave examples. The theorem is that, so what does this filtration have to do with what I was talking before? It is actually it determines the asymptotics. So if V I T alpha, this is a representation of some Q, and we have this Y, or we have central charge, maybe. These are these numbers Ci, essentially what I had before. Then, so what we do, so we have this, I remember, so if I have a metric on here, there's some flow I can apply to the metric. So if H is h of t is a trajectory of the flow. This was this minus, I think it's gone now, but it was this h minus 1, h dot is equal to minus argument of something. Then, so I mean, what's happening so this is not converging to a fixed point, it's not converging to a metric, but there's kind of a compactification of the space of metric, which is filtration. So, I mean, what's going on is like the metric is degenerating on some sub-piece of the filtration. And then so you look at that sub-piece, and then again it's degenerating on a further piece. So it determines a limiting filtration. Limiting filtration is determined by h. So it's independent of initial metric you choose, which also a priori also, is the, yeah, so I should say, so it is this something which is maybe the iterated weight filtration. So what I mean by iterated is generically it's the same thing that I defined in this theorem, but maybe I should add here. So this is just a filtration by real numbers, not by this R infinity. So where does this R infinity come from? It's some iterative construction. Right, so if you look over there, the condition was that this x tilde in a tilde is semi-stable. So there's an iterated filtration. Which would be sort of this thing here determines the leading term in the asymptotics, and then this the next term, which is as follows. So if this x tilde in here is not wholly stable, that means it's not semi-simple in, so we continue, again apply the theorem to x tilde in the category of things of the same slope. So if it's not polystable, that means it's not semi-simple in the category, subcategory of a tilde of things with slope pi over 2. So by replacing, sort of a gets replaced by a tilde pi over 2. And you pull back this, so this, continue this construction, this determines actually a filtration not just by real numbers, but by this R infinity. So you don't need to prove a new theorem, you just apply it again and again. And so I've said maybe that before. So the limiting filtration of this flow is then the same iterated filtration, and the growth rates of this metric restricted to the lambda piece. What was it? My object was let's say x is representation. Filtration on here. The indexing of the filtration determines the growth rate of the metric. So is lambda. If you take your representation, you restrict to the sub-object, which is determined by some index of this filtration. the metric there grows with some rate, and it's just the index of that piece. Maybe to make that more clear, I'll give an example. It's more concrete. So if so the simplest case where there's something going on is if you have your representation is the A2 quiver, so this representation of A2, a two-dimensional indecomposable thing, then and there's some numbers, there's some parameters y1, y2, and then the filtration is the only one here you can really write down, which is this simple object sitting inside the thing, the full representation, and the weights. There's some weights lambda 1, lambda 2. The index, these growth rates of the metric, which will satisfy lambda 1 is lambda 2 plus 1, and then this balancing condition, y1 lambda 1 plus y2 lambda 2 equal to 0. And so the difference here in grading is 1. That means that look at asymptotics of the metric log h. There's some metric here, h1, h2, so essentially just a positive real number. And then log h1 over h2 is like log of t. So that the two associated graded pieces here are distance 1 apart. That corresponds to this coefficient 1 in front of the log t. And a more interesting, this is essentially like this example with the nilpotent operator, which is just a single 2x2 block. Essentially meaning it's the same modular lattice. So here again, the filtration, I mean the degree in which the associated gradients sit here depends on this function y, but the actual filtration is always the same. It's always the same two-step filtration. So there's no kind of wall crossing in this case, but another example where there is wall crossing is something A4 quiver. This kind of zigzag orientation of arrows. And then here, so there's a wall and chamber structure. If so here there's some wall crossing, and I'm almost out of time. I won't describe complete detail, but you can ask me later about y1. So one chamber is where y1 times y4 is less than y2 times y3. You get a two-step filtration. And then if y1, the opposite inequality in the other chamber, you get a four-step filtration. And if you're exactly on the wall, this is where these next logarithmic, where this kind of iterated construction comes into play. So where you don't, the growth rate is not just some log t, but it's, we'll have these double logarithmic terms. So if on the wall, these are equal, then there's again a four-step filtration. But it's indexed by R2, so by log t, R times log t plus R times log t. So if you apply this theorem the first time, it gives you a two-step filtration. This object here is not semi-stable, so you can apply the theorem a second time, and it refines it to a four-step filtration. But that's only happening on this wall for non-generic behavior. So the if you want to know more in detail what this filtration actually is, you can talk to me. But I'll just mention that for now and say some kind of the outlook. So what can you do with this, or what do we hope to do with this filtration? Which again, so it's always, in any case, you have sort of, whenever you have a Haiden-Simon filtration, you get this theorem gives you that there's this canonical refinement. So it's something defined quite generally, but what do you use it for? So first of all, so actually in general, there will be some wall and chamber structure on this space of y's. So this HOM from k0 plus to r greater 0. It looks like these. So here the wall is some quadric. I think in general it will be some real algebraic geometry, so just a real algebraic equation with integer coefficients. But we don't fully understand this wall and chamber structure yet. But besides that, well, first of all, so how do you use the Haiden-Simon filtration? Gives you kind of a stratification of your moduli stack of objects by type of filtration. And so here you get again a stratification by the type of filtration on the moduli stack of objects, which may be interesting to look at. It's kind of like a Morse theory, sort of. And second, so going back to this analogy that I had in the beginning of the talk, right? We think of this flow on quiver representation as like a toy model for this flow on Lagrangians. And actually, there's also a B model flow to that, which is Donaldson heat flow. So A model and B model geometry. So I would say this is, of course, conjecturally for now because it's some statement about asymptotics of solution to a PDE, nonlinear. But the strong indication for why there might be a relation is because this filtration is not just coming from this quiver geometry, it's actually coming from just the category itself, right? It's completely abstractly defined, so it would be strange if there's another filtration yet that should be relevant here. So what does this mean? Maybe, so again, so B model should be this Donaldson heat flow, kind of a bundle, which is an extension of stable bundles of the fixed slope, and I'm looking at the limiting filtration of that bundle under the flow. And A model, it means something like I have some special Lagrangians of the same slope, so maybe spheres, and then I can sort of deform slightly away from their sum. So I do some surgery, introduce some necks, make it a Lagrangian, their kind of sum. And so meaning that they're the same slope means if I apply the flow to this kind of configuration, these necks will shrink under the flow and sort of they converge back to the union of all these things. So this is here under the flow. We'll go to the union. So these necks, they shrink at some rates, and the conjecture is that the speed at which you have some configuration of Lagrangians, the speed at which they shrink, so the asymptotics of the flow in this semi-stable case, are again determined by the same filtration. I mean, that's a big question for now, but I think it's, so far, something at least interesting to look at. There's also one-dimensional version of that, which is with the curve shortening flow. I'm going to stop here. So, thank you.